So I think now we can continue our review session here. So last class, we mainly went through some examples on the unit conversion, right? So it's not only converting the air pollutant concentrations, you can also use this concept in some engineered processes, for example, drying of the fabric. So after we talk about the air pollution or air pollutants and this unit conversion, we started to learn about the PM, right? So the first thing we learn about the PM is the log normal size distribution. So we mentioned that typically these PM won't be able to follow a Gaussian distribution, mainly because for Gaussian distribution, there will be particles with a size below 0, right? That doesn't make any sense. So that's why instead of directly using the dP, we used log dP in the distribution. So in this way, we can guarantee that the particle size is larger than 0, right? So actually, one of the quite important feature that we mentioned about for the log normal distribution is the semi-log plot. Okay, so basically the semi-log plot is a plot that looks like this, right? You have the x-axis being the cumulative fraction of the particles, y-axis being the particle size, right? So if you recall, for one of your homework problems, you're asked to make sure a certain size distribution follow a log normal size distribution. And I saw that a few of you actually hand draw this semi-log plot. Okay, so y-axis follows a log scale. But on the x-axis, it is quite special because it's not a linear scale in terms of the x-axis. So if you notice here, you see it's more crowded near around 50%, right? And then when it expands to the lower fractions or higher fractions, it basically stretches, right? So it doesn't follow a linear increasing pattern. So that's why you can't use your hand drawing to make sure this is a semi-log plot. And actually, this relationship follows the error function that we talked about in the class. So there are a few extra slides talking about the error function, how we make this semi-log plot. If you're interested, you can go through that. So basically, that's in our slides that's talking about the log normal distribution of the particles. Okay, so with this semi-log plot, we can use that to confirm whether a size distribution follow a log normal distribution. So the way we do that is just to see whether the points that we get, for example, from the impactor measurements, whether they follow a straight line. So if they follow a straight line, or in general, they follow a straight line, we can say that they follow a log normal distribution, right? So there are some other information that we can also extract from this semi-log plot. So we mentioned that basically for the semi-log plot or the log normal size distribution, we know that at 50% of this cumulative fraction, that will correspond to the particle, basically the geometric mean of the particle size, right? So basically, if a log normal distribution follow this pattern, then if we want to ask what is the DPG or geometric mean size of the particles, we can know that it's probably around 9.8 micrometer, right? So we also mentioned that at 84.1%, basically this is 50%. At 84.1%, that will correspond to the particles who has a size of DPG multiplied by sigma g. So sigma g is the standard deviation, geometric standard deviation of the size distribution, right? So for example, if we plot out where this point is corresponding to, it is approximately 22 microns, right? So we also mentioned that 15.9%, that will be DPG divided by sigma g, okay? So basically around 15.9%. We have the DPG divided by sigma g that's having a value of approximately 4.5 microns. right? So based on this relationship here, we can calculate what is DPG and what is sigma G. It is quite straightforward here that we can get 50% is 9.8 micrometer, right? And then by using these two equations, basically we can multiply them all together. DPG squared is equal to 22 multiplied by 4.5, right? Micrometer squared. We can take the square root of this equation and then just calculate out what is DPG. It's highly likely that it's not going to have the same answer with this, right? But they're going to be close. So what you can do is basically you can calculate the DPG by averaging these two values, right? Divide by 2. It doesn't matter. Actually, if you get the correct answer or exactly the same answer, you can just use that. If they differ by a little bit, you can just take the mathematical mean of the two sizes, right? So the way we calculate sigma G is just by dividing these two equations, right? Sigma G squared is going to be equal to 22 divided by 4.5. So this is how we can calculate the sigma G out of this semi-log plot, right? So basically, if we show you a plot that has this feature here, you can get quite many important parameters out of it. So this method, you can also use it reversely. So for example, if I tell you what is DPG and what is sigma G, you should be able to give me what is the feature of the size distribution, right? So if you recall, for this homework problem, I noticed that some of you had actually had some questions on this. So let's spend maybe 1 minute to look at this problem here.
Hey,
and just
Dr.
think
Wang.
about, yes?
Will we need to have copies of this graph printed off before our test?
So I already uploaded to the Canvas. So I haven't sent a notification yet. I was thinking maybe after this class, I can send a summary of the midterm, let's say the extra information about that.
Okay, so it'll say what we need to print off beforehand?
Yeah,
Okay.
you need to print it out, yeah.
Okay, thank you.
Yeah.
Hi, Dr. Wang. That file is actually not available.
What's it?
The file is available, but it's not visible, so it cannot be printed.
Oh, it's not visible yet?
Yes.
Let me take a look after the class.
Okay, sure.
Yeah. Okay, so let me get my notebook. I can get these things written down. Yeah, let's spend some time looking at this problem, okay? All right, so I think we can talk about this problem now. So I noticed that some of you, when you solve this problem, you actually refer to the original definition of the log normal distribution. So saw that some of you actually did this. So we basically plotted out the distribution of the log normal distribution. And of course, I think most of you who use this method were using hand-drawn curves, which is really not accurate, right? You cannot get some accurate results just by roughly drawing out the distribution. Okay, of course, if you use, let's say, Excel or use some online plotting tools to get this log normal distribution, you may be able to calculate what is the fraction. But I would say the most straightforward way to solve this problem is just using the semi-log plot, right? So it already mentioned that the log normal distribution has a dp50, which is the size of the particle corresponding to the cumulative fraction of 50%. So we know that this is dpg, right? dp50 is 8 microns, and sigma g is 3.0, right? So if we see these parameters, we should respond quickly that we can plot out 3 data points on this semi-log plot, right? So we should know that basically 8 microns will correspond to 50%. We can find it out here, right? So this is due to the property of this log normal distribution, right? So we should also know that 84.1%, that will correspond to 3, basically dpg multiplied sigma g, which is 3 multiplied by 8, is 24 microns. Okay, we should find out where is 84.1, is somewhere here, and then 24 micron somewhere here. Okay, so I noticed that we don't have very accurate ticks on the label here. You can just be basically approximate here, right? So finally, the answer won't differ by quite a lot. Okay, so this is dpg multiplied sigma g. We should also know that 15.9%, we have dpg divided by sigma g, which is 8 divided by 3, right? I think that's basically 2.6 or 2.67 micrometer, right? That's somewhere here. All right. So with these 3 data points, we can draw a straight line. They should also follow a straight line here. Otherwise, it's not log normal distribution anymore. So you should probably use a ruler to do this. Okay. And then see what this question asks us about. It wants us to plot the distribution and also determine the mass percent of the particles below 2 microns. And it is quite straightforward once we have this plot. We just need to find out where 2 micron is, right? 2 micron is here. Just take draw a vertical line here. And this is maybe around 11%. Okay. So instead of using this entire log normal shape here, which is really not accurate here, we can just use the semi-log plot to deal with this problem. Okay. Any questions on this? So if not, yeah, so basically this is how we can look at this problem. Okay. And then if not, we can go to the next section, which is about the drag force. Okay, so I mentioned that basically I urge all of you to memorize or to recite basically what is the equation of the drag force. So we mentioned that drag force, if it's in the Stokes regime, that's 3 pi mu dp divided by c multiplied by VR. Okay, so really, I mean, this class doesn't need a lot of reciting work or memorizing work. Okay, so try to bear this equation in mind. It will help you a lot when during the exams. Okay, so basically in this equation, we mentioned that the mu is the viscosity, dp is the particle size, c is the Cunningham slip correction coefficient, vr is the relative velocity. Okay, so also remember that this is not absolute velocity, this is relative velocity. Okay, so also mention that for the slip correction coefficient, when the particle size is much larger than the mean free path, for example, particle size above 1 micron, then we can treat C as 1. Okay, so basically, if the particle size is very large, mainly above 1 micron, then we can just ignore this C term here, right? So with this equation, we can look at what is the gravitational settling behavior of the particles, right? So basically, when the particles settle down, it's just the drag force balanced with the gravity. mg will balance with the drag force. So based on this relationship, we can calculate what is the settling velocity, right? So we can just do mg equal to 3 pi mu dp divided by c multiplied by vr, right? And then further, the m here is volume multiplied by particle density, right? So that's pi over 6 dp cubed multiplied by rho p. So if we plug in this relationship to here, right? So we can calculate that the settling velocity will be equal to dp squared rho p multiplied by g multiplied by c divided by 18 mu. Okay, so this is the settling velocity. You don't have to memorize this equation because you already know what is the drag force, right? This is just a equation derivation here. Okay, so this is the settling velocity when we assume that it's in the Stokes regime, right? So with this equation, we can look into these problems, right? So this is also one of your homework problem. Maybe we can spend another minute looking at this problem here and think about how we solve this. All right, I think this problem is quite straightforward, right? So it's just asking us to calculate what is the terminal settling velocity. So we already have the equation here, right? The only thing is we can make some approximation when we deal with this problem. Because let's say for the first one, actually for all the questions, you notice that the particle diameter is pretty large, 20 micron, 5 micron, and 40 micron, right? So what this means is that when we calculate the behavior of the particles, we can just assume that the Cunningham slip correction factor is equal to 1. We don't need to go through the equation to calculate what is the mean free path, right? Because the equation for the mean free path is quite complicated. And also for the C, it's a function of the particle size and mean free path. So that's also quite complicated. I think you guys have went through there in your homework problems. So for this problem, by just looking at the diameter, it's larger than 1 micron. So we can assume that the Cunningham correction factor is 1, right? So this will simplify our analysis here. So here again, I will derive the equation for the settling velocity, right? So basically we'll equate the gravity with the drag force, right? So we'll put in gravity equal to 3 pi mu dp. Originally we have to divide by c, right? But here, because the particle size is larger than 1 micron, we can assume that c is equal to 1. And finally, we have the VR, which is the relative velocity of the particles. And because the air is stagnant, right? So that's why when the particles settle down, this relative velocity will be the settling velocity going down, right? So if we again plug in the equation for the mass of the particle, pi over 6 dp cubed rho p multiplied by g equal to 3 pi mu dp multiplied by VR, right? And then these can get canceled. We have 2 here, pi get canceled, right? So we have VR equal to dp squared rho p g divided by 18 mu, okay? So this is the equation to calculate the settling velocity, right? So we have, let's say for each question here, we have the particle size ready, right? We can plug in that. We have the G ready, okay? So let me just change the color here. So we have the particle size ready, G ready, the air viscosity, right? We can just use standard standard condition, right? So that's typically around 1.8 or 1.9, multiplied by 10 to the negative 5 Pascal second. Okay, so this is also standard units. And then the only thing we don't know right now is the density. So the density is related with this specific gravity. So I think in the class I mentioned that this specific gravity just means the ratio between the particle density over the water density. So for example, if this particle has a specific gravity of 2, then that simply means that the density of this particle is 2 multiplied by 10 to the third kilogram per meter cube. Okay, it's twice of the density for water. So I saw that some of you actually directly plug in the particle density as 2 kilogram per meter cube. So you get very, very small answers for the settling velocity. Okay, so actually this is a very small value because the air density, we're not talking about the particles, the air density is around 1 kilogram per meter cube. Okay, so 2 kilogram per meter cube is highly likely to be another gas. Okay, so typically if we're talking about solid, the density will be somewhere around the water density. Okay, or at least the order of magnitude will be similar to water, which is 10 to the third kilogram per meter cube. Okay, so I saw that some of you get the wrong answer, mainly because of the specific gravity here. So once we have all of these parameters, we can just plug them in and then calculate what is the settling velocity. Okay, so for example, let's say, yeah, for example, if we're talking about the 20 microns here, I'll just use this space to do the calculation. Okay, VR equal to dp squared rho pg divided by 18 mu. So we can just plug in everything in the standard units. So 20 micron will be 20 multiplied by the 10 to the negative 6, right? Squared. Multiplied by 2, multiplied by 10 to the third. This is the density, right? And then multiplied by 9.8. This is the gravity. And then you divide by 18, multiplied by 1.84, 10 to the negative 5. So this is also the standard units, okay? So if you use the calculator, you can find out that the final answer is 0.0237 meter per second. Okay, so one thing you need to bear in mind is that everything has to be in the standard units. Otherwise, you won't be able to get the correct answer. Okay, so all the equations are built upon the same set of units. Okay, so this is about the gravitational settling. So after that, we talk about basically several types of these PM removal devices, right? So the first thing we learned about is the settling chamber. It's basically using the same mechanism as the gravitational settling, right? So we give a few examples on how to calculate the efficiency, right? We mentioned that the efficiency is basically VT divided by H, right? If you recall, we have basically a cubed chamber, right, filled with particles, and the particles will settle down with a certain velocity. That's the settling velocity, right? So the efficiency is just basically how fast they settle down, multiplied by time, right, and then divide by the height of the chamber. So let's say if time is infinitely long, the efficiency will reach to 100%, right? So then we give a few different geometries. We mentioned that in industry, we're not going to build a chamber for this settling process, right? So we typically will use duct. So the duct will have a flow velocity of U, a height of H, and the length of L, right? So we mentioned that for this thing, we just need to plug in the value for the time. So the time will be equal to L divided by U, okay? So basically for a horizontal duct, we have V divided by H multiplied by L divided by U. And the V here is the settling velocity. This is a horizontal duct. So we give an example that when it is a tilted duct, is facing up, right? We have basically we'll separate the gravity into two directions and then consider what is the situation there. So in our homework problem, I actually got quite many questions about this final answer here, okay? So we mentioned in the class that if the tilted duct is facing up, it's quite difficult to predict what is going to be the result in terms of the particle collection efficiency or particle removal efficiency. But if it's a duct that's facing downwards, there is one certain answer, okay? So the efficiency will be lower compared to the horizontal duct. So the major reason is this, okay? So we can do a very simple derivation here. So if you recall, this is our, basically this is our efficiency for a horizontal duct, right? So I'll just copy it here. Eta is equal to VH multiplied by L divided by U. Okay, so further, this V here is the settling velocity. So mention that the settling velocity is just mg divided by 3 pi mu dp. Okay, recall that we basically will set up a balance here, right? So that's how we calculate this settling velocity, okay? So for this tilted duct, things will be a little bit different. So first, in terms of the settling, let's say we're analyzing the movement of the particle here, okay? So it's having a gravity that's trying to pull it downwards, right? And then if we separate the direction of this force here, it's going to have a force that's perpendicular to the base. So basically this force is going to drag the particles to deposit or to settle onto the base of the duct here, right? So we also have a fraction of the force that's pulling the particle in this way. So basically the particles will try to, will have another extra force to pull it outside this duct, right? So if we separate this gravity here, mg, we know that this is theta, so this is going to be mg cosine theta. And here, for this form, that's going to be mg sine theta. Okay, so now how do we calculate this efficiency here? So we're going to use the same form of the efficiency. Okay, so let's say we just forget about this angle here. Let's treat it as a horizontal duct, except that this person, say originally, this person will observe in this way, right? Let's say we start to observe in this way. Okay, so let's treat it still as a horizontal duct. So what you can see is that basically there will be an extra force that's pulling the particles in this way, right? Pulling the particles to exit this duct here. So basically, originally the particles will just flow with the flow here. We'll just go with the flow, and now it has an extra force. So what that means, the particles will just move faster, right? So how faster it is, we can again equate the drag force with this force that's pulling it outside the duct. So the way we do that is just balance the drag force with this extra force. Mg sine theta will balance the drag force in this way, right? And then we can find out that's basically 3 pi mu dp multiplied by Vr equal to mg sine theta, okay? So Vr is going to be mg sine theta divided by 3 pi mu dp, okay? So now let's do a substitution here, okay? So we already showed that this V under the horizontal duct condition is equal to mg divided by 3 pi mu dp, okay? So basically we'll have the relationship that here is going just to be equal to V multiplied by sine theta. So remember this V here is the settling velocity under the horizontal duct condition. So this is the relative velocity. So we mentioned that when a particle is inside a flow, to calculate its absolute velocity, we need to consider what is the flow velocity, right? So the absolute velocity, let's say the v, let's say in this direction, x direction, y direction. So Vx is going to be equal to u plus Vr, right? And this is mainly because there's an extra force to pull the particles outside the duct, right? So we have u plus v multiplied by sine theta. So this is the velocity of the particle that's traveling along the duct. So now if we want to calculate how long it can stay in this duct, so time will be equal to L divided by u plus v sine theta. So this is going to be the time that the particle will stay in this duct, right? And then also how fast does it settle down? The velocity that the particle settle down is dependent on the force that's perpendicular to this duct here. So for that, we can again equate with the drag force, right? Because the drag force is going to pull the particle upwards, right? We can calculate a velocity that's perpendicular to the duct, which is trying to let the particle settle down, okay? So for that velocity, that's just going to be mg cosine theta divided by 3 pi mu dp. Okay, so this is the velocity in the y direction, vy. Okay, so now we have everything to solve this problem. We mentioned that the efficiency is just v multiplied by t divided by h, right? For any duct. Now we know that the v here is basically the force that's pulling the particle towards the base of the duct. So we have, again here, we can make the substitution, right? Mainly, let's say to differentiate from others, let's assume that this v here is a v bar, okay? We have basically vx is equal to u plus v bar sine theta, vy equal to v bar cosine theta. Okay. So now we have v bar cosine theta divided by h, and then multiplied by t, which is L divided by u plus v bar sine theta. Okay, so it's getting quite crowded here. So this new efficiency, let's put it outside, okay? V bar divided by h multiplied by cosine theta multiplied by L u plus v bar sine theta. Okay, so this is new efficiency for this tilted duct that's facing downwards. Okay, this is eta t, right? We know that the eta horizontal is quite simplified. That's just v bar L divided by hu, right? So now let's just compare these two efficiencies. For the tilted duct, you see in the denominator, we have one more thing here, right? So the denominator becomes larger, and that is going to make the tilted efficiency go lower, right? And furthermore, in the denominator, we have a cosine theta. Cosine theta is below 1. So that's going to basically further make this tilted duct, the efficiency of the tilted duct becomes lower, right? So that's why for this tilted duct, the efficiency will be lower compared to the horizontal duct. And it is actually quite straightforward. Let's think also outside the box. Okay, so we have been using these equations to think about the scenarios. Let's think outside the box. Let's say if there are particles suspended in this duct, okay? So now we're talking about the removal of the particles. So basically the force that's trying to drag these particles towards the base becomes smaller, mainly because this theta here, right? We have a smaller force to let the particles travel in this perpendicular way. And we also have a larger force to drag the particles outside the duct, right? So basically the particles will spend a shorter time in the duct. And at the same time, the force that's settling these particles becomes smaller. So under this combined effect, the efficiency will become smaller, right? So one extreme condition is, let's say we make this angle to 90%. If we have 90% duct, we're just introducing particle in this way. It's not going to settle down anything on the side of the duct, right? So the efficiency will become lower compared to the horizontal duct. Okay. Any questions on this problem? I think I wrote these equations all over the place, maybe a little bit difficult to catch up. Okay, so if you have any questions, try to go through the video after the class and then try to understand what we're talking about here. Okay. So this is the gravitational settling. And after that, we talked about the cyclones. So we did quite a few examples in our class about the calculation for the cyclones. So basically, the important equation is the calculation for the DPC and eta J, right? So the DPC is dependent on the detailed design or the geometry of the cyclone here. So again, everything should be standard units. So I noticed that only a few, actually for this homework, only a few of you, maybe 3 or 4 of you, who didn't get the correct answer for the DPC. I think it's mainly because of the units you plug in into the equation. Okay, so you have to use the same set of units, no matter whether it's standard units or British units. You need to make sure that they're under the same set of units. Okay, you can't mix them up together. So in this equation, a lot of things are dependent on the geometry. For example, the W, which is the width of the inlet, right? So NE, that's the effective turns for the gas flow in the cyclone. Excuse me. So VI, that's the inlet velocity, right? The particle density and the gas density, right? Viscosity, we also need to plug it in. So typically for the DPC, you should expect somewhere to be 1 to 10 microns, okay? So if you get a 10 nanometer for the DPC, then there is something wrong going there, okay? Or if it's, let's say, millimeters in the DPC, then there's something going wrong, okay? So try to make sure that when you calculate DPC, you get the correct answer. So once you get the DPC, you can calculate basically the efficiency at any different size, right? So for example, in this problem, it wants us to calculate the overall collection efficiency of the particles with a certain size distribution, right? So we mentioned that for this problem, we need to first find out what is the DPJ. So that's just the average of the size bins, right? So that's 0 plus 2 divided by 2. This is 1, this is 3, 5, so on and so forth, right? So once we have the DPJ, we should have the eta J, right? So we can calculate that based on this equation. So for particles inside each size bin, there's a specific efficiency in there, right? So this column that's going to be provided to us, that is the mass fraction of certain size bin, okay? And we mentioned that to calculate the overall efficiency, we need to multiply this eta J with mj. Because when we remove the particles, we need to consider how many particles are there, right? So what is the mass of the particles in each size bin? And then we'll take the summation, mj eta J, and then divide that by the total mass, mj. Okay, so with this equation, we can calculate what is the overall collection efficiency. All right, so I won't go through the details in this calculation. We have done that in our class talking about the cyclones, okay? So of course, you need to refer to this table because if we're talking about the conventional cyclones or the Lapo type of cyclones, you need to use this these geometry factors to calculate some parameters. For example, the eta E here, and also the width of the inlet, right? The width of the inlet. You need to find out these parameters. Okay. So after the cyclones, we talk about the ESP. So for the ESP, I have to say that for the ESP and backhouse filter, it involves more practical designing, right? So for example, in this problem, this is, I think it's in your previous homework. So we're trying to design a ESP that has certain efficiency, okay? And then it also gives us a flow rate, the effective migration velocity, and then it wants us to calculate how many plates we're going to need, right? Maybe we can spend half a minute to look at this problem and think about the solutions. Okay. I think due to the time limit for this class, we have to go a little bit faster now, right? So the central equation for the ESP is basically the Duct equation, right? We introduced that in the class. That's basically eta equal to 1 minus exponential of minus WEA divided by Q, okay? So for any ESP, it should follow this equation here, right? So that it's dependent on the effective migration velocity, the area, the total active area of the plate, and also the flow rate, right? So once we have the efficiency, we can start to plug in all of these parameters. So you see it's quite straightforward. We have the efficiency, we have the flow rate, we also have the migration velocity. So we can actually solve out, find out what this A is, right? So if we plug in, that's going to be 0.98 equal to 1 minus exponential minus 6 centimeters divided by second, multiplied by A, divided by Q, that's 5,000 meters cubed per minute. Okay, so I carried all of these units here, mainly because they're not in the same set of units, right? One thing is in second, one thing is in minute, one thing is in centimeter, one thing is in meter cubed, right? So we can basically convert one of these into the same set of units, right? Or the more direct way is change everything into standard units, right? So in this case, the migration velocity will be 0.06 meters per second, right? And then in terms of the gas flow rate, that's going to be 5,000 divided by 60 meter cubed per second, okay? So we need to make sure that everything is in the same set of units, and I prefer standard units in these equations. Okay, so once we have this equation, you can find out that the A is 5533.4 meters squared, okay? So this is not the end yet. This is the minimum area or the active area of all the plates. So we mentioned that to calculate how many number of plates we need to think about several things. So first is the mechanical fields, right? So mechanical fields, we use the number of mechanical fields, we use M as the number, right? We need to first basically equate this number with M multiplied by N minus 1, right? Multiplied by AP, right? So the M is the number of mechanical fields. We need to minus 1 for the number of plates in each mechanical field, mainly because we're not using all the plate area to solve the collection efficiency, right? So for all the arrangement of the ESP, we know that the outside of the ESP is not being used. Let's say for the inside plates, we're using both sides, but for all the two plates at the start and at the end, we're not using the area. So that's why we'll minus 1 here, right? And then calculate the product. And since here we have M equal to 3 AP, that's the plate area on both sides. That's 2 multiplied by 6 multiplied by 10, right? This is a plate area. And we calculate out that n is equal to 16.092. So we mentioned that to achieve this collection efficiency, we have to round it up to 17, right? So we have the number of plates in each mechanical field. So the total number of plates will just be m multiplied by n. 17 multiplied by 3 is 51. Okay. So now it's total number of plates, and then we need to look back on what is the, so first we have the required plate area, and the actual plate area will just be n multiplied by AP, right? So that is the plate area, or the actual plate area, right? So basically, this is how we design a ESP system, right? And then finally, for the backhouse, I graded some of the homework problems. So I think the major issue is finally in the practical design of the compartment. So for detailed derivation of these calculations, you can just refer to our previous class there. But in terms of the practical design, I think the final answer for this question, when you calculate the number of bags in each compartment, you can find out that it is close to 319. Okay, so that's my impression. Maybe this is for another problem there. So, but let's say, for example, this is what we get from the answer. Let's say we get 318.5, right? So we know that to guarantee the collection efficiency, we need to round it up to 319, right? But 319 is not divisible by anything, right? We are not going to build a wall of the backhouse here. Mention that we have to build a backhouse that has certain squared geometry, right? So because of that, we need to further round it up to 320. So some of you actually stop here for this problem, but actually we need to come up with a practical design. We need to say it should be arranged in this geometry, 16 rows, 20 columns, or 20 rows, 16 columns. So we need to give this practical design as a final answer. We can't just give this number here and stop it there, okay? So that's the common problem that I saw in your homeworks. So if you have more questions on the homework problems, just let me know. Again, I want to say that the midterm is going to be quite similar to homework problems. I'm not going to give you very difficult ones that you won't be able to solve in let's say, 30 minutes, okay? So that's all for this class. Just let me know if you have any questions. I'll post this video online. Yes?
Excuse me, the exam around 5 problems or 4?
It's either 4 or 5. I haven't decided yet.
Okay, thank you.
It's going to be dependent on how difficult the problems are. Other questions? So if not, that's all for this class. And there will be no homework for next week, right? So just spend some more time going through these homework problems. All right? You guys have a nice weekend.